Hello. In this video, we're going to cover Stokes' theorem. All right, so let's start off by saying, suppose we have a vector field that defines a vector at every point in R3. Suppose we have a closed curve with counterclockwise orientation. That borders a surface with positive, and by positive we mean outward, orientation. Let's go through and draw ourselves pictures, make sure we understand what we're talking about here. Suppose we have a curve, it's a closed curve, and it borders a surface. So we need to draw a surface that is attached to this. Let's go through and do, how about this? Something like that. And that surface has outward orientation. And so with outward orientation, if you have a shape like this, a curved shape like this, where there's a maximum, then outward is upward. If we had a downward facing, like a minimum, then you'd have downward facing. And so the way to represent that on here is I'm going to go through and I'm going to put little normal vectors. It just means we have upward pointing normal vectors. Okay, and then to show the counterclockwise orientation, we can put little arrows on the curve. And it's counterclockwise when viewed from above. So if you were looking straight down on it, you would see a counterclockwise rotation. And we've got these upward pointing normal vectors. Okay, so what is Stokes' theorem? Stokes' theorem says that if we go through and calculate f dot dr, then that equals the double integral across the surface of curl of f dot n ds. Or if you use the shorthand, curl of f dot ds. Okay, so that is the statement for Stokes' theorem. If we were to go through and write this out, so what is it saying? What is this? What is this? Why are they equal? Or what are we saying here that in terms of their equality? Let's go through and write that out. So what is Stokes' theorem? And so we start off, we have the left-hand side, which is this f dot dr over c. So in a previous video, we went through and discussed this. This is a circulation or a rotation integral. So it measures the amount of rotation in the vector field f along the curve c. So it measures the degree of rotation. Okay, and then so what is this other thing? So we've got, let's think about it for a second. So we've got curl of f dot n ds. So what is this? So it may not be obvious what this is. We'll discuss it a little bit more to go through and establish this. But what this is it's a measure of rotation at points that are on the surface. So in one case, we've got a measure of rotation. We've got how much rotation is there along, C? To what degree is there rotation? If we look at the vector field, to what degree do the vectors from the vector field point in the same direction as the curve? So how much rotation is there along the curve? And then for the other part, the second part, it's saying if we want to go through and calculate the rotation at all of the points that are on the surface and you add all those rotations up, then they add up to the same amount as the rotation along the edge. So that's what the theorem is saying, going through, if you compare rotation along the border and you compare it to the rotation on the inside, then those two are equal. So that's the idea. Whether that makes sense or not, I mean, you might need a little bit more explanation than that, but they do both have to do with rotation, right? Curl of f is a measure of rotation. We discussed that in the curl video, and dotting it with the normal vector. So I'll explain in a minute how that does end up getting you the rotation that's at a point. And so we've got rotation at points, rotation along the edge, and one ends up equaling the other. So Stokes theorem says that these are equal. Why? Why would they be equal? Other than just what I just said, which is that they both have to do with the rotation. Well, the reason is the same reason as Green's theorem. Say why? Why would this be true? Same as Green's theorem. And if you've watched our Green's theorem video, I go into a great deal of explanation of that. I'll give a slimmed down version of it, and then we can go through and extend it to Stokes theorem, and then we'll discuss the one little nitpick that makes the two different. They're actually very similar. I'll make that more obvious in a second. First, let's go through and reestablish, why is Green's theorem true? If you go through and draw yourself a picture, I want to try and squeeze both of the two theorems on the same page here. I don't know how good a job I'll do that, but trying to leave it big enough so we got another room for the other one below. All right, so I'm going to take Green's theorem, which is in 2 dimensions, and I'm going to draw it in 3 dimensions and just put it on the XY plane. Right, so normally it's in 2 dimensions, but we can go through and take something in 2 dimensions and we can just draw it flat on the XY plane. All right, so what Green's theorem says, we have a closed curve C. It surrounds a region, which we'll label D. All right, so we'll say this is region D. And it says that if you go through and add up the curl of f dot k at every point, if we add those up at every point inside of here, then we'll end up getting this value. This is the sum of the curl of f dot k, and in the Green's theorem video, we go through and we prove, we go through and we show that this is the rotation at a single point. Or sorry, it's the rotation around a small square. It's the sum of the rotation around patches. That's the word I used in the other video. That's a good reason. It's a good reason to have notes, like this little square. So the idea here is if we go through and cover this with patches, then this will be the sum of the rotation on those patches. All right, so let's go through and do that. So I'm just going to go through and draw lines going across here. We cover it in patches. Let's draw lines going the other way. Okay. And then if we go through and calculate the rotation around one of these little patches, so I'm putting, these are supposed to be arrows. Still didn't make them quite big enough. So if you go through and calculate the rotation around that patch, that equals the curl of f dot k. So the rotation around a patch is curl of f dot k. If you go through and do a double integral, that means to just add up all of them. Okay, so we can go through and this is the sum of the rotation around the patches is this quantity. All right, so that's one result that we get for this. However, a second result that you get is that if you go through and actually add up the rotation around the patches, right? So if we go through and take this rotation here and we add up the one next to it. So you'll see I've got arrows in both directions on this piece. What's going to happen there is that this piece will end up canceling because you have pieces, you have rotations in opposite directions. Those are going to, one's going to be positive, one's going to be negative, and that's going to cancel. And so if you go through and actually go through the process of adding up this curl of f dot k, if you actually start doing it, what'll happen is you'll see you'll get, oh, I got a cancellation there. If you go through and do the one next to this one here, you can see, oh, double arrows there, this cancels. If you do this one here, oh, we got cancellation here and here. And what happens as you actually go through the process of adding up all of these rotations, all of these inside parts of the rotation eventually cancel. And the only thing that you have is the exterior, right? And so if you go through and you actually add up, right? If we go through and we add up the rotation on the patches, all the inner parts, all the inner pieces cancel. Until the only thing that we have left is just the outside. And what's the outside? F dot dr, right? And this is established better in the Green's theorem video, but that's the very simple idea here, is that if you go through and think about these independently, like individually, the rotation around this patch is given by this, and you could just say, I'm just going to go through and add all those up. That would be going through and summing them up, you know, over our region D. That's what the double integral represents. It represents a sum. But then if you actually go through and add them up and you start doing them one at a time, you'll discover, oh, wait, wow, that's also this thing happens where all the inner pieces cancel until you just actually get just the exterior. And so that is why the two would end up being equal. I'm going to do something a little unusual on here. And that is I'm going to go through and I'll actually put the k vector on here. And so the idea is that this rotation, it's around vector k. Notice if I put the k vector on here, right? So this is around k. This one's around k. That's going to be relevant when we go through and do Stokes theorem. So the rotation here would be around k. Sorry, the k's are a little bit difficult to see. But the idea is that you could go through and you could put vectors on here, and the rotate, and if you put them at this here at the center of the patch, then the rotation around the edge of the patch is around vector k. And so that's going to be relevant when we go and look at Stokes theorem. So let's do that right now, actually. So that's why Green's theorem is true, is because, actually I've already said it twice, so I won't say it a third time, but this, you add up the sum of the rotation around the patches. If you actually do it, the inner pieces cancel. All right, so what would how would this be relevant to Stokes' theorem? All right. All right, let's see if I can draw ourselves a good picture here. My notes look amazing. It's difficult. How about, that's pretty good. It's pretty much the way that I did it in my notes. And then we got to draw our surface. And then let's go across this way. Okay, and so you can kind of see the surface. Now what I'm going to do is just like I took my region here, my region D, and I ended up cutting it into pieces. I'm going to go through and I'm going to cut our surface into pieces as well. All right, so to do that, we're going to go through and do this. And then let's go across the other way. Not bad. Not quite as good as in my notes, but we'll have to do. All right. So the idea here is that I've done the same thing I did here. I just did it on a surface instead of on this flat. I guess you'd call this a surface, but on this flat surface, I'm doing the same thing here on our curved surface. Okay. And now if you go through on here and you were to go through and calculate the rotation around one of these pieces, right? If we were to calculate the rotation around this piece here, it turns out that that rotation around that piece is given by curl F dot N. Okay, if we go through and do a bunch of those right across, if we do that for all of the patches, then what we're going to get is we're going to get the double integral S ds. This is going to end up being the sum of the rotation around the patches. Okay. And if you go through and do this, just like above, if we go through and actually start, so this is this double integral is individually, it's adding up the rotation around these patches, but it's not thinking about what happens at, when you actually go through the process, when you actually do them collectively. If you do that, then similar to our Green's theorem example, if we go through and say, take this patch that's next to it, and we add up the rotation on that patch, all right, what happens? We have, oh, this inner piece cancels just like it did with Green's theorem. If we go through and do this guy here, this piece cancels because we have opposite pointing, vectors. And if you go through across the entire thing, all of the inner pieces are going to cancel just like they did with Green's theorem. We actually go through and add up the rotation around the patches. All the inner pieces cancel. Until what's left? If all the inner stuff it cancels, eventually the only thing that's left is the border. And so we're going to end up with integral of f dot dr. Okay, so in terms of going through and kind of comparing these two, you can see how the two could work the same way. When we went through and established Green's theorem and proved that this was true, An important part of that proof was to go through and show that the rotation around one of these individual patches was this curl of f dot k. So we have not gone through and established that the curl of f dot n is the rotation around the patch. We're just claiming that. However, if you go through and look at these, there are some cool similarities. So if you go through and actually, like I did just a moment ago, I put the k on here. It's the rotation around k. That is what the curl of f dot k is it's the rotation around k. If I go through and take a spot here, let's say in the middle, and I put my normal vector, which is very difficult to see. That's the problem with drawing on the, again, maybe the picture is too small. But if you put the n on here, you can see the rotation here is around n. Okay, so, curl of f dot n is going to be the rotation around n. If we go through and do the guy next to it, right, you put an n there. What is going to be the rotation? That would be curl of f dot n. Okay, the rotation around n would be given by these little arrows. And so you can see the similarity. Here we've got rotation around k is given by this. Our claim is the rotation around n is given by this. So what we're claiming here is we're claiming that it's consistent. We're claiming that if you just take k and replace it with n, then you end up getting the same thing. So that's not completely unreasonable, right? So we did prove that curl of f dot k is the rotation around k for greens. And then we're claiming that curl of f dot n is the rotation around n. So we're claiming that it basically just behaves the same way. And so that's something that, I'm going to go through and spend a little bit more time talking about than just claiming it's true, but it's not completely outlandish that it would be true, that there could be some consistency there. So let's do that now. Let's go through and spend a little bit more time talking about it, trying to convince you that these two things would do the same thing and that you could just pop k out and put n in and you'd end up getting the same idea, except one is in 2 dimensions and one is in 3 dimensions. Oh, by the way, I did forget to mention this. So the way I interpret Stokes theorem versus Green's theorem is that Green's theorem is in 2 dimensions and Stokes theorem is in 3 dimensions. It's basically an extension by 1 dimension of Green's theorem. So we've got Green's, which is f dot dr equals curl of f dot k dA. So there's our Greens, and then we've got Stokes. And we've got curl of f dot dr equals, f dot dr equals curl of f dot n ds. So they both essentially say the same thing. One says it for a flat object, one says it for a curved object. So the flat object could be interpreted as just in 2 dimensions. And when we discuss Green's theorem in that video, everything is in 2 dimensions. Of course, and then we extend it into 3 dimensions for Stokes theorem. And so that's how I see it, is that Stokes theorem is the extension of Green's theorem by 1 additional dimension. Okay, so let's go through and see if we can discuss this curl of f dot k, curl of f dot n piece, because that's the only piece really that you'd need some explanation of. Once you have that curl of f dot n ds is the rotation around here, then you can see it that after that all of the effects from Green's theorem do happen. All that cancellation happens, and we just end up with the rotation around the exterior. And so that's what we really need to talk about more. Okay, so let's just go through and draw ourselves some pictures. So we've got a flat. So this is supposed to be flat on the XY plane. We've got a flat patch. If we put arrows on it, we've got counterclockwise rotation around it. We're saying if you went ahead and tossed a k into the middle, then the rotation around k is given by curl of f dot k. The rotation around the exterior of the patch is the rotation around k and is given by curl of f dot k. Now, we established this in the Green's theorem video. I actually went through a little mini proof, and showed that this is true. This is just going through and restating that piece from Green's theorem. So what we're saying for Stokes' theorem is that if you took this and you tilted it, it would still be true. So if we took it and instead of having it flat on the XY plane, we went through and drew it. Tilted so that it's basically kind of like a patch that's sitting on a surface instead. And we went through and said, here's the normal vector. Here's the rotation around the exterior. And what we're saying is the rotation around the exterior of the patch is the rotation around n and is given by curl of f dot n. Okay, so this is what we've proven. We've done this one, check. This one remains, is it true? Can we go through and just replace the k with n and it would work exactly the same way? Let's go through and see if we can prove that. Oh, well, maybe not prove it. Explain it, why that would be true. So to go through and explain it, to think about it, just to kind of think your way through it, the question you have to ask is, what does it mean to find the dot product of curl of f and a vector? So what does that mean, right? So why, what does it mean if we go through and do curl of f dot k? I mean, we showed that it's the rotation around the exterior, but why? I mean, is there any logic to it? Is it just a result, or is there some sensibility there? And it turns out that there is. If you go through and actually think your way through it. So what is the curl of f? So if we start off with that, the curl of f is the vector around which there is rotation in the vector field. Right, assuming there is rotation. So if we have rotation in the vector field, the curl of f goes through, it finds the rotation, and you end up getting a vector around it. Right. So the idea is that if we have some rotation in the vector field, we got some rotation, then what curl of f does is it goes through and it produces a vector. So this vector here, this is the curl of f. Okay, so that's what it means to calculate the curl of f. It's the vector around, around which rotation occurs. So it's basically in the middle of the rotation. All right, second fact here. So that rotation, the curl of f, it is orthogonal to the plane containing the rotation. So if we took this rotation here and we just put a plane around it, which looks suspiciously like a patch, we end up getting the curl of f is orthogonal to that plane of rotation. Okay, next fact, right? If you go through and calculate the dot product between two things, the dot product is large when those two things are in the same direction. So if we go through and calculate the dot product between curl of f and some vector, so that's going to be large when curl of f and u are in the same direction. That's just the way the dot product works. So if you recall from our dot product video from the beginning of the semester, if you go through and calculate the dot product between two things that are orthogonal, you get 0. If you calculate the dot product between two things that are parallel, you get a maximum value. Okay, so what does that mean? All right, so you could, if you imagine, we've got our rotation in the vector field. We've got here's our curl of f. We have our comparison vector, a second vector, a vector u, right? And so this situation here, this would represent a large result where the two are parallel. Okay, and so this is going to end up producing a large result for curl of f dot k. Oops, sorry, curl of f dot u. A little Freudian slip there, because that's where we're going next. Okay, and so the next part is the part that's maybe a little bit strange here, but if this is the curl of f and and you've got rotation around it, and we've got u, and we've got a large result for curl of f dot u, which represents the situation where those two are parallel, then what you can do is you can take u and you can replace it in the curl of f. You can replace it where the curl of f is. And so in this picture where the curl of f is, I'm going to put u, and we can end up getting that this is the rotation around u. So if curl of f dot u is large, which means that u and curl of f are parallel, then you can replace curl of f with u. And what this will do is it will give you a measurement for how much rotation there is around u. All right, let me try and write that out. It says, so if you do go through and do that, this would be equivalent to curl of f dot u will be large when there's rotation in the vector field around u, around vector u. Thus, curl of f dot u can be interpreted as a metric for measuring rotation around u. Okay, so let me go through that one more time here. So we start off, we've got curl of f dot u. We know that's going to be large when curl of f and u are parallel, when they're in the same direction, when the picture looks like this. And what we're saying is that if that's the case, that curl of f and u, if that curl of f dot u is going to be large when they're parallel, then curl of f dot u is going to be large when u replaces curl of f and you're measuring the rotation around u. And so curl of f dot u can instead of being interpreted as whether curl of f and u are parallel, it can be interpreted as a measure of whether there's rotation around u in the vector field. And so basically it enables us to turn the curl of f calculation, it enables us to turn it into a function where we plug in vectors, we plug in u, and curl of f dot u tells us how much rotation there is around u. Okay, and so that's the idea here, is we're extending from thinking of curl of f and u as two separate things to thinking of the dot product here as giving us a measurement of whether the two are parallel. And then if they're parallel, then one could replace the other, and we could shift it into being a measure of rotation around the input vector u. Anyway, that's the idea, is that you could go through this process in terms of analyzing what the curl of f, the dot product between curl of f and a vector is. So curl of f, dot product between curl of f and a vector, it can be interpreted as a metric for whether there is rotation around that vector. Once you get to that point, you can then go through and pop in vectors and interpret them. All right, so thus we could go through and we could pop in what is curl of f dot k. It is going to give us a measure of rotation around k. And if we go through and draw the picture, which I've drawn a couple times, but if we just draw the picture here, what is rotation around k? Rotation around k is going to look like this. Oh, and that suspiciously looks like rotation around the patch. And so we know this is true. We already have proven this result. We already shown this result that curl of f dot k is a measure of rotation around k. So the previous couple pages in our thought experiment through what it means to dot product curl of f with a vector, it does prove true in the one situation that we have actually sat down and analyzed. And so at this point, what we're going to do is we're just going to, we can now feel comfortable saying that we can extend this so that curl of f dot n is a measure of rotation around n. Again, we're doing the same thing. We're popping n into our previous result with curl of f dot u, and we're saying, okay, so this should give us a measure of rotation around n. All right, well, if you go through and draw yourself a picture of a patch that's in 3 dimensions instead of sitting flat on a surface, if we go through and put n on there, what does the rotation around n look like? It looks like this. Oh, and that matches up with our rotation around the edges of the patch. And so we can say that the rotation here is curl of f dot n. Okay, and so that goes through and establishes the one piece that really would maybe give you some skepticism from our explanation here, and that is that the rotation around the patches is curl of f dot k, and the rotation around the patches here is curl of f dot n. So that's the justification that I'm going to give in terms of why you could take this and extend it. Is if you go through and just go through the analysis of what it means to dot product curl of f with a vector, what it means is it means to go through and measure, is there rotation around that vector? And once you've got that, then that can go through and establish our 2 previous results, the one that we know is true and the one that we want to be true. Okay, so that's essentially the proof or the explanation for why Stokes theorem is true. I didn't go through and do an x sub I, y sub j, and all that other kinds of jazz. It's actually really complicated in this particular case with a 3-dimensional surface to do that, which is why I didn't. But instead we're just going to go through and accept the result, with the explanation that's given. Okay, so what are we going to do with Stokes theorem? There's 2 types of problems that you can go through and solve with Stokes theorem. Let's go through and write it out here so that we can actually point at it. All right, so with some problems, they're going to start you off and they're going to go through and they're going to say, use Stokes theorem to evaluate this double integral. If they're asking you to use Stokes theorem to evaluate a double integral, they don't mean to evaluate the double integral directly. What they mean is they mean for you to go through and evaluate the line integral, right? If they say use Stokes theorem, it's implied that you're going to go through and find the other side from the side they give you. So if they say use Stokes theorem to find this, they really want you to use this. If they say use Stokes theorem to find the integral of f dot dr, then they want you to go through and do the double integral. Okay, again, why is that? Well, if they wanted you to go through and use the line integral to evaluate this circulation integral, they would just say go through and calculate the integral of f dot dr directly. If they say use Stokes theorem to evaluate f dot dr, then that means to use the fact that this equals this and use the other side. Anyway, that's something that students commonly find very confusing and strange in the language, but that's the way that it's done. All right, so let's go through and do some example problems. All right, so here's one we could start with. So we're given f equals I plus x plus yz j plus xy minus square root z k. We're told C is the boundary of the part of the plane 3x plus 2y plus z equals 6 in the first octant. And the instructions are to go through and use Stokes theorem to find the integral of f dot dr. Okay, so what I was just saying is if they go through and they give you some stuff and they say use Stokes theorem to evaluate, they don't want you to evaluate the line integral. If they wanted you to evaluate the line integral, they just would have said, find this, no Stokes theorem. The fact that they're saying use Stokes theorem to find the integral of f dot dr means to use it, and by using it, we know that f dot dr equals the double integral. So what we want to find is the curl of f dot n ds. Okay, so this is what we want to go through and do. We want to go through and find curl of f dot, and I'm going to use the shorthand here, ds. When we actually go through and evaluate these, this is what we end up using, is we use the curl of f dot ds. But in terms of explaining why Stokes theorem is true, it's helpful to use the dot n for the similarity to Green's theorem. Okay, so if we're going to do this, there's a few things we need to do. We need to go through and figure out what the surface is. Once we've done that, we can find the ds, which is what we did in the last section with the surface integrals. We need to go through and calculate the curl of f. Once we've got those, we can dot product them and then integrate. All right, so what is our surface? What surrounds? So C surrounds the surface. We need to go through and figure out what that surface is. Let's go through and draw a picture on this page. And we'll do the problem on the next page. All right, so what is the surface? C is the boundary of the part of the plane. Oh, so the plane is the surface, okay, in the first octant. And so we can go through and graph that by The easiest way to do this is just to set two of the variables to 0 and solve for the third, and that'll get you the intercept. So if y and z are 0, then you get 3x equals 6. So we're going to get an intercept of 2 on the x-axis. If x and y are 0, then z is 6. If x and z are 0, then y is 3. And so this is our, so that's our surface. It's a flat surface, which is a little weird, understandably, because we've gone through and we've been talking about curved surfaces. However, Green's theorem is limited to flat surfaces that are on the xy plane. So this is it's a flat surface, it's a plane, but it's not flat on the xy plane. And so we need Stokes theorem for this object, because again, it's not on the xy plane, it's not flat on the xy plane. All right, and so here's our, this is 3x plus 2y plus z equals 6. So C is oriented counterclockwise. And so we're going to want upward pointing normal vectors. So we want n to point up. And so in this case, that means we want ds also to point up using the information from the last section on surface integrals. Okay, so once we've got that, let's go to the next page and actually do the problem. All right, so ds. So ds, since we have our surface defined in terms of x, y, and z's, we don't need to use the parametric definition, parametric surface definition. We can go through and we can use a definition in terms of x, y, and z. To go back, which one should we use? Do we want to have z by itself and have a function of x and y? Do we want to have x by itself and have a function of y and z? Typically, what I tell students is that if you can, it's best to go through and have z by itself. If you can, if that's easiest. If we had a z squared here, I would not do that. I would not get z by itself, because by getting it by itself, you're going to be creating two separate functions. But we just have z to the first power here and y to the first power and x to the first power. You could get any of these by themselves. So I think the easiest in this case would be to go through and get z by itself, in which case our ds formula is going to be negative partial of z with respect to xi minus partial of z with respect to yj. And if this part is confusing, then you need to go back and watch the surface integral video. K and then plus k. So that's going to be our ds. To go through and calculate this, we do need to go through and get z by itself. So let's just do that. We'll do it right here. So we have z equals 6. Actually, let me do it this way. It doesn't matter how you do it, but I'm going to do it this way. Negative 3x minus 2y plus 6. And so if we went through and calculated z differentiated with respect to x, we would get negative 3. So ds is going to equal negative 3i. And then we're going to have minus, and then what's the partial with respect to y? That would be negative 2. J, and then plus k. So when we go through and calculate this out, we're going to get 3i plus 2j plus k. Okay, so that's our ds. That's the first halfway there. The second thing we need to do is we need to go through and calculate the curl of f. So we've got curl of f. All right, and so that's going to be I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And what are our components? We've got 1 for I. And then we've got x plus yz. And then for k, we have xy minus root z. All right. And then we can go through and calculate those. So we've got I, that's going to be the partial with respect to y of xy minus root z, which is x. minus the partial of x plus yz with respect to z. So that's going to be y minus j. That's going to give us the partial with respect to x of xy minus root z. That's y minus the partial of 1 with respect to z, which is 0, plus k. And then we get the partial with respect to x of x plus yz, which is 1, minus the partial of 1 with respect to y, which is 0. Okay. And so now we can go through and just pop those in. So we want to go through and find curl of f dot ds. We're just going to pop those in. So we'll have x minus y I plus, minus, actually, let's just do this, minus yj plus k. Then we want to go through and dot that with our ds, which is 3I plus 2j plus k. All right, then we're going to integrate over our region, which is all the xy values that the function would take on. So we need to integrate across the xy values. So that's going to be, here are the xy values. We want to integrate across that. So we'll just say that's D. All right, and so before we do that, we go ahead and just do the dot product here. So we're going to have x minus y times 3. So that'll give us 3x minus 3y minus y times 2. So that's going to give us minus 2y. And then plus k. So I got k dotted with k. So that's going to give us plus 1 dA. So what have we got? We've got double integral over d. That's 3x minus 5y plus 1 dA. Okay, if we had had any z's in here, so this is something that came up in the last section on surface integrals. If we'd had any z's in here, we would have substituted to get rid of them, and the substitution we would have used to get rid of those z's would have been this. Okay, so you use your surface definition to go through and get rid of any z's that are in your double integral. With a double integral, we can only have 2 variables, not 3. All right, so we need to get down to 2 variables. Okay, so let's see if we can go through and actually finish doing the problem here. We've got our double integral, 3x minus 5y plus 1. Let's go through and determine an order of integration. So when we're integrating across D, what you can do, like we've done all semester, you could redraw this in 2 dimensions. So you've got x goes to 2, y goes to 3. We've got our line. And so you can look at that, is that type 1 or type 2? In terms of doing double integrals, that's what we do. We figure out type 1 or type 2. In this case, it could be either one. And again, what I tell students is if you have a choice, do it type 1. So type 1, you have a vertical rectangle that you're using to go through and sum up the area. So we want to go top to bottom. So for the top, we need an equation that is in terms of y equals. And to figure that out, what do we got? This is a y-intercept of -3, and then we've got a down 3 over 2 slope, sorry, +3. And then so we've got down, so -3/2 x down 3 over 2, and then with an intercept of 3. So this would be our equation. So we want to go through and integrate. That's going to be our top bound. And so we're going to have 0 to -3/2 x plus 3, right? -3/2 x plus 3, yep. And then we want to do that from 0 to 2. So we got dy, dx. And so now it's just some simple integration here. We're going to get 3xy minus 5/2 y squared plus y, 0 to -3/2 x plus 3 dx. Pop that in. got 3x times negative 3 halves x plus 3 minus 5 halves, negative 3 halves x plus 3 squared plus negative 3 halves x plus 3. And then simplify. That's what we've got here. This is going to be negative 9 halves x squared plus 9x. There should be an x in here, which we forgot. So this is going to be 9/4 x squared times negative 5 halves. So we're going to get negative 45/8 x squared. And then what do we got there? So then negative 3x times 3 halves x times 3 times 2. So we're going to get negative 9x times negative 5. So we're going to have negative 45 halves x. And then we've got 9 times negative 5 halves. Negative 45 halves. And then minus 3 halves x plus 3. And let me just check my notes here. Okay, everything looks good here. And then we can go through and just combine like terms 0 to 2. So negative 9 halves and negative 45/8. So we can multiply by 4/4 here to make this into negative 36, negative 81/8 x squared. And then we've got 9x and negative 45x and negative 3 halves x. All right, so that's going to give us, we got negative 45 halves and negative 3 halves. That's going to give us negative 48 halves, negative 24, negative 24 and 9. So we get negative 15x. And then finally plus, oh, nope. Finally, we've got negative 45 halves and then plus 3. So that's going to give us 6 halves. Negative 37 halves x. Sorry, negative 37 halves. All right. Okay, I had to pause it because I'm like, just had to recheck this. All right, so I see some mistakes in here. So this should have been a plus 45 halves. And so this is going to be a plus 30x, I believe, right? So we're going to get 42 over 2. That's going to be 21, 21 and 9. That's going to give us 30, actually, not 15. Jeez. All right, and then that should be a 39. If we take negative 45, positive 6, that gives us negative 39 halves. Okay, and I think we got it now. Hopefully. If not, people can let me know in the comments. But this is kind of plug and chug busy work. I'm just going through it and getting the answer just in case people want to check their work. So we got x cubed over 3, 15x squared, 39 halves x, 0 to 2. So it's going to be negative 81/8 times 8/3 plus, and then here we're going to have 60. And then 39 halves times 2 is going to be negative 39. These cancel. Okay, and then let's see, what do we got here? So this is negative 81/3 21. Then 3 goes into 81 27 times. And so we end up with -6. Okay, that looks right. Let's do another one before I spend too much time staring at that one and find more mistakes. Let's do another one. So we've got f x, y, z equals 2yi plus x, z, j plus x plus y, k. C is the curve of intersection of the plane z equals y plus 2 and the cylinder x squared plus y squared equals 1. All right, and again, we're asked to go through and use Stokes theorem to find f dot dr. Okay, so again, if we're asked to use Stokes theorem to find f dot dr, that means we're going to actually calculate the other side of Stokes theorem. So we're going to go through and find curl of f dot ds over the surface. Okay, so to do that, this is a couple step problem. We need to go through and find ds. And again, so you need to figure out what's your surface. So it's the curve of intersection of the plane. All right, so let's just draw ourselves a picture here. So maybe that will help. So we've got a cylinder, x squared plus y squared plus 1 or equals 1. All right, and we have a plane, z equals y plus 2. Okay, so the way that you can go through and graph this plane, the fact is that there's no x, which means that it extends in the x direction. When that happens, I usually go through and graph the object where x is 0, and then you can just slide it back and forth for different x values. All right, so where x is 0, we'll start there. We've got, sorry, that should be a z. We've got the y value here. If you just go through and plug in y equals 0, you'll get a z-intercept of 2. So we can go 1, 2. So we got a z-intercept of 2. If we go over to y is -1, plug in y is -1, you're going to get z is 1. And you could plug in z is +1, and you'll get z is 3. Right, and so this is what our plane looks like as it's going through and cutting through those points. And now if you slid it over in the x direction, it's going to hit, okay, if it slides over, it's going to hit this part of the cylinder here at that point. And if you slide it the other way, it's going to hit the part of the cylinder here at that point. And so if you just go through and kind of, you know that the edges are curved. If we just draw a curved edge going through from this point to this point to that point, that should get us the front edge of the object. And if you draw a curved edge going through this point, and that point, they'll get you the back edge. All right. And so what we've got, C, this is C, right? So this is the curve of intersection. Let's go through and just maybe draw a little squiggly, this is C. If that's C, what surface does that border? What surface does that border? It borders the plane. So the plane is the surface in this case. If the plane is a surface and we've got Z by itself, then we're going to want negative partial of Z with respect to Xi minus partial of Z with respect to Yj plus K as our formula for ds. And we can use Z equals Y plus 2 for that formula. Popping that in, we're going to get ds equals the derivative with respect to x is 0. So we get no I component. The derivative with respect to y is going to be 1. So we're going to get negative j plus k. It's going to be our ds. Actually, so this would be this. All right. And then we also need to go through and calculate the curl. So curl of f. That's going to equal I, j, k. And we need partial with respect to x, partial with respect to y, partial with respect to z. We've got 2y, x, z, x plus y. So we're going to get I times 1 minus x minus j times 1 minus 0 plus k z minus 1. All right. So let's go through, and that's our curl of f. We've got our ds. Let's go to the next page and dot product them. So we're going to have 1 minus xi and then negative j, and then z. Oh, and then where any z's we want to replace, right? Because we want to get down to 2 variables. So we want to replace z with what z equals, which is y plus 2. So we're going to have y plus 2 minus 1k. And then we're going to dot that with negative j plus k over d. And d is going to be the shadow of our object. We'll discuss that in a second. Actually, let's just go ahead and simplify this. So we got y plus 2 minus 1. That's going to be y plus 1. All right, so let's simplify this. We've got y 1 minus x, and then there's no I component, so that just goes away. Minus j dotted with minus j, that's going to give us 1. And then we have 1 y plus 1 with y plus 1. So that gives us y plus 1 dA. And so we end up with y plus 2 dA. Okay, and let's just check this because that is not what I got in my notes. So we got 1 minus x. All right, I think I found it. This should be a z minus 2. Right, so for k, we've got partial of xz with respect to x, which is z, minus the partial of 2y with respect to y, which is 2. So that should have been a 2. And so we should have had a here instead of, so we've got z minus 2, so that should be y plus 2 minus 2. Okay. And then if we go through and do that, those are going to cancel. And so we've got d 1 minus x I minus j plus y k negative j plus k. All right. So we get 0 and then 1 plus y. And hold on. I'm going to ahead and pause it again because that still does not agree with what's in my notes. Okay, I've checked it and this is correct. My notes are wrong. Oh, goodness. All right, so what is D? So D is going to be all of the XY values that are inside of inside this red circle here. When we do double integrals, what we want to do to get the region that we're integrating over is you just want to take that region and just, think about the shadow of it or think about flattening it. What would that look like, that red circle, if we went through and just put it down onto the XY plane? It would cover the circle directly beneath it. It would cover this. So that's going to be our region of integration. So we want to go through and integrate across that. Of course, that is a circle. And so what we do with circles when we change the order of integration is we go through and change them to polar coordinates. So we want to go through and rewrite this into polar coordinates. The way that you do that, you use the translation formulas: x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. You get the idea. All right, so in this case, y is going to be r sine theta. And then we have r dr d theta. And our region, this is the circle of radius 1, right? And so we want to integrate from 0 to 1 and then 0 to 2 pi. All right, let's see if we can do this. So we've got, this is going to be, I guess we'll do it in 2 steps. It's r and then r squared sine theta, dr d theta. So 0 to 2 pi, antiderivative here, we're going to have r squared over 2, r to the 3rd over 3, sine theta, 0 to 1. So that's 1/2 plus 1/3 sine theta. And we're so close, but I guess we'll do this on the next page because there's just nothing here. So the antiderivative of this would be 1/2 theta minus 1/3 cosine theta. Right, what do we got? Plus sine theta, antiderivative sine is negative cosine. And then we want to evaluate that 0 to 2 pi. So that's going to give us 1/2 times 2 pi, that's pi. And then here we're going to have minus 1/3 plus 1/3. This is going to end up canceling. And so we're going to end up with just getting pi. All right, just giving another look. It looks good. Let's go on to the next one. We've got f equals e to the xyi plus e to the xzj plus x squared zk. And we're told S is half the ellipsoid for x squared plus y squared plus 4z squared equals 4. That lies right of the xy plane. Or sorry, xz plane. Oriented in the direction of the positive y-axis. And we're told to use Stokes theorem to find double integral curl of f dot ds. All right, and so as with the others, if they tell us to use Stokes theorem to find this, then that means we want to find the other side of Stokes theorem. So what we're actually doing here is calculating f dot dr for this situation. All right, so let's figure out the situation we've got. So we've got half of the ellipsoid, and so this guy, it's the half that lies to the right of the xz plane. Okay, so to go through and graph this, the easiest way to do this is just to plot a bunch of intercepts. If we go through and we make y and z equal to 0, then we're going to get the x-axis, and we're going to get 4x squared equals 4, which is x equals plus or minus 1. So we've got 1 and 1, negative 1. All right, so those are on the object. And if you go through and do the same thing with z, you get 1 and 1. All right, and so what we've got is we've got a circle on the xz plane. And then for y, if x and z are both 0, your y are going to get plus or minus 2. So we go 1, 2. And so there's our object. All right. So there's our surface, and we need to figure out what is the curve that borders that surface. And if you look at the picture, the curve that borders that surface is going to be the circle. Okay. So that's what we want to integrate across when we go through and do the problem. We need to make sure when we do that, that it is oriented properly. It needs to be oriented counterclockwise relative to the direction of the surface. So the direction of the surface, the positive orientation for the surface is the positive y-axis. That means that if you're looking down the y-axis, we want to see counterclockwise rotation. So it should look like this. That is counterclockwise, looking at it from the right. Okay, so how do we do that? How do we go through and evaluate this? Well, if you remember back, it's been a few sections, but evaluating line integrals, you need to go through and find the, you need to go through and parameterize the curve. And once you've parameterized the curve, then it's just a matter of substituting into f and dr. All right, actually, we could do that right here. We don't need to turn the page just yet. So if we're going to parameterize that curve, how do we parameterize this? All right, well, we need to go through and pick some stuff. When we've got circles and we're trying to parameterize a circle, we can go through and we can use polar coordinates for that. So we get x equals r cosine theta. And then normally we would do y equals r sine theta, but instead we could do z equals r sine theta. And then we've got x squared plus z squared equals 1. And although you rarely use it, tangent of z over x equals theta. So we go through and use our polar coordinates. And if you do that, you'll notice, well, this circle, the red circle here, if we were to write out its coordinates, it's x squared plus z squared equals 1. So we have, whoops, little Freudian slip there. That's supposed to be r squared. Cheating, little cheating there. All right, it's x squared plus z squared equals r squared. And then we also know that x squared plus z squared equals 1 from the picture. And by substituting that 1 in, we can go through and say that r equals 1. So we substitute that in, we get r equals 1 by taking this one and by taking this equation and comparing it with that equation and seeing that the right side is r squared for 1 and the right side is 1 for the other. So r equals 1. All right. Sorry about that. Once you do that, you then take that and you plug it in. And so you're going to get x equals cos theta and z equals sine theta. So that is our parameterization of the curve. Oh, and then the third coordinate, you say, oh, well, what about y? Y is 0, right? Y is 0 for that curve. So there's our, we've gone through and parameterized the curve. Now we can go through and use that on the next page. So we're going to get our curve over C. So first, take your parameterization of the curve and pop it into your vector field, right? So we're going to have, we have E first, and it's to the xy power. So what is x? X is cos theta, y is 0. So we're going to get cos theta times 0. All right. Oh, and don't forget, this is I. And then e to the xzj. So xz is going to be these two things multiplied together. So we're going to get e to the sine theta cosine theta j. All right. And then what about x squared z? So x is cosine. So we're going to have cosine squared times sine. Okay. All right. And then we're going to go through and dot that with dr. All right. So the curve here, once we've parameterized the curve, you can turn that into a vector function. You can turn that into r of theta. All right. So that's going to be cosine theta I plus 0j plus sine theta k. And then if that is r, we want dr, so you need to differentiate that. So dr, so you take the derivative of cosine, so we're going to get negative sine theta I, 0j, and then plus cos theta k. So we've got negative sine theta I plus cosine theta j. Okay, negative sine theta I plus cos theta k. All right. Theta. And then, oh, we need the bounds. What bounds do we want? So we want to go 0 to 2 pi. All right. Let's go ahead and do this. So e to the 0 is 1, 1 dotted with negative sine theta. It's going to give us negative sine theta. We don't have any j components. So that's 0 dotted 0 multiplied by that. So that goes away. And then we've got plus cosine cubed theta sine theta. Okay. D theta. All right, just a second here, because again, this disagrees with my notes. All right, I checked it and I figured out why it disagrees with my notes, and that is that I forgot to go through and check that this is oriented counterclockwise. All right, so if you go through and plug in 0 into this for theta, what are we going to get? We're going to get 1i plus 0k. So 1i plus 0k, where is that? Let's go through and use a different color here. That's right here. That would be 1, 0, 0. If we go through and plug in pi over 2, you're going to get cosine of pi over 2, which is 0, plus sine of pi over 2, which is 1k. So then you're going to get this point. So we went from here to here when we plugged in our values. All right, that's wrong. We've got the wrong rotation. All right, so how do you fix it when you have the wrong rotation? Well, the easiest way to do it is you can swap sine and cosine. Well, I mean, that's not the easiest way to do it. That's how I do it, is I just swap sine and cosine. If you go through and swap these, all right, so we're going to have sine theta here and cosine theta here instead. Now, if you go through and plug it in, if you plug in 0, you're going to get 0, 0, 1. That's this point. And then if you plug in pi over 2, you're going to get 1, 0, 0, which is this point. And so now the rotation is correct. If you go through and differentiate these, the derivative of sine theta is cosine theta, and the derivative of cosine theta is negative sine theta. All right, and so now we can go through, and so this is supposed to be cosine theta, and then that one is negative sine theta. Yep, and then if you go through and multiply those, here you're going to get cos theta. And then here you're going to get minus. Actually, we need to change these two. Sorry, these are no longer correct. All right, let's go back. Sorry. E to the xy. We got x is sine, y is 0, so it's going to be sine theta times 0. And then next we've got xz, that's there we go. That's going to be sine theta cosine theta. And finally, x squared z, that's going to be sine squared cosine. And finally, again, sine cubed theta cosine theta. And now it agrees with my notes. All right, 0 to 2 pi cosine theta, 0 to 2 pi sine cubed cos theta. This is sine theta, 0 to 2 pi, which is 0 minus 0. So we're going to get 0 from that part. And then here we want to do u substitution, sine. U equals sine theta, du equals cosine theta. Don't forget that negative. Take 0, plug it into sine, you get 0. Take 2 pi, plug it into sine, you get 0. And so this is the integral from 0 to 0 of u cubed du, which is 0. So we got 0 from our first integral, 0 from our second integral, 0 plus 0 equals 0. And so we get 0. All right. I did one more. We got y equals e to the zi plus xy sine zj plus x cosine z k. And we have S is the hemisphere. X squared plus y squared plus z squared equals 4, z greater than or equal to 0. And again, use Stokes theorem. To find curl of f dot ds over our surface. All right, and so when you're told to use Stokes theorem to evaluate the double integral, that means we actually want to find f dot dr. Let's go through and sketch our object. So it's the hemisphere. So hemisphere, we've got 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Top half of the sphere. Looks like that. Z greater than or equal to 0, top half. So that's going to be our surface. Here's our curve that surrounds the surface. We need to go through and so this is going to be the curve. We need to go through and parameterize that. So to do that for C, we could just do our normal x equals r cosine theta, y equals r sine theta. I actually intended to do these problems in the opposite order, to do the easier one first, where you have x and y and then extend it to x's and z's, but well, best laid plans. All right, and then we've got x squared plus y squared equals r squared, and tangent of y over x equals theta. All right, so we've got all that. This circle is given by, it has the equation x squared plus y squared equals 1. So just like the last problem, we could go through and just pop the 1 in place of the r squared. And so these two together tell us that r equals 1. Using that, you can take that and pop that into this equation, and then we can turn C into x equals cos theta, y equals sine theta. Putting those together, we can create a parametric, our vector function form. So we're going to get cosine theta I plus sine theta j. And this time we will not forget to check, is it oriented properly? All right, so let's go through and plug in theta equals 0. If theta equals 0, then cosine of theta is going to be 1 and sine theta is going to be 0. 1, 0 is here. All right, and then if you plug in pi over 2, cosine of pi over 2, 0, sine of pi over 2, 1. So we're going to get 0, 1, which is here. So we've got this rotation from viewed from above. That is counterclockwise, and so this is perfect. All right. Using that definition, we can go through and find dr. Dr is going to be negative sine theta I plus cos theta j d theta. All right, and so from there, to go through and evaluate this, we'll jump to the next page now. To evaluate this, we need to figure out what f is. To figure out what f is, you're just going to take your definition for f and you're going to pop in your parametric equations, your parametric equation values here. So let's do that. So jump into the next page. We've got f. What is f? It is y e to the z. Well, there's no definition here for z. Z is going to be 0 here. We've got z is 0. And so if z is 0, you're going to get y, which is sine theta e to the 0, which is 1. So we're just going to get sine theta I. All right. And then next, we're going to have xy. Well, that's going to be sine cosine, but then sine of 0, which is 0. So that kills that whole term. And then plus, we're going to have x, which is cosine, and then cosine of 0, which is 1. So we're going to have cosine k. All right. And then we're going to dot that with our dr, which is negative sine theta I plus cosine theta j. And it's 0k d theta. And then our theta values to go all the way around the circle are 0 to 2 pi, 0 to 2 pi. If we go through and dot these, we're going to get negative sine squared theta. All right, and let me check the heck, because I can, of course, my notes disagree with that. So we've got cosine theta. Oh, okay. I think I see the mistake here, or a mistake. This was the circle of radius 2, not 1. We got 2 there. All right, so we're supposed to have 2 cosine theta, 2 sine theta, 2, 2, negative 2. Plus 2. All right. Does that fix everything? Let's take a look. So we should have a 2 here. And a 2 there. Those should be 2s. All right. Let's check one more thing here. Yeah, my notes are wrong. You know, why bother doing these problems ahead of time? You're just going to completely ignore your notes, and they're going to be wrong half the time. All right, I think we got it though. So this should be a negative 2, and that negative, I missed it in my notes. Right, so if we do x is 2 cosine, y is 2 sine, then when you differentiate cosine, you get negative sine. And I think it's correct now. All right, to go through and do this, you got to pull out the negative 4, 0 to 2 pi. You do the double angle identity here. It's 1 minus cosine 2 theta over 2 d theta. So we get negative 4. And then the antiderivative here is going to be 1/2 theta minus sine 2 theta over 4, 0 to 2 pi. So we're going to get negative 4. So this guy is going to be 0 at both ends. And so we're going to get 1/2 times 2 pi, which is going to be pi. And so it looks like we get negative 4 pi. I gave it another look. It looks good. People in the comments can go through and tell me whether I made any additional mistakes. But looks like negative 4 pi. I'm going to say that's the answer. And that is the video, and it's probably at least one example too many. Wow, that took forever. All right. Thank you for watching. See you next time.